This lecture is dedicated to the major experimental facility of the NICA complex, the facility that has served as the basis for the name of the facility. It is a collider for heavy ions and light polarized nuclei. The collider of the NICA complex is one of the world's most interesting and perhaps most remarkable colliders. But in order to realize this, it is necessary to mention the main characteristics of other colliders, as well as the different types of experiments. What is the basic idea of a collider? A collider is a colliding beams facility. You might wonder what the primary motivation of high-energy physics was to invent such a specific way of conducting experiments. And furthermore, how were experiments in nuclear physics originally performed? Scientists started noticing the appearance of accelerated charged particles. They could be taken either from a radioactive source, like in E. Rutherford's first experiments, or from some accelerator facility, and directed towards a target. After that, results of the particle interaction with the target were studied. Meanwhile, particle kinetic energy is, unfortunately, not fully utilized for the creation of new particles. A part of the kinetic energy of a flying particle transforms into the kinetic energy of fragments as the result of an interaction. The fragments from the interaction, the new particles, which one would actually like to study, move in the average direction of the flying particle. During the process, the energy that is applied for the creation of new particles is approximately proportional to the square root of the energy of the flying particle. We diligently increase the particle energy in the accelerator, but we can produce new particles with rather low efficiency. How to avoid this? Two particles may be directed towards each other. Then the kinetic energy of each particle will fully transform into the energy of newly emerged particles. The energy of accelerated particles would be used with maximum efficiency. The first to come up with this idea was one of the geniuses of accelerator physics and technology, Ralph Widerow, who started inventing accelerators as a schoolboy, when accelerators were not yet in existence. In 1943, he patented the idea of performing an experiment on colliding beams. This idea was about 20 years ahead of its time. In 1943, the phase stability principle had not yet been discovered, and there had not been any modern accelerators which could be used to implement experiments on colliding beams. The idea of an experiment on colliding beams was proposed in the 60s by Gersh Butker and Donald Kirst. That proposal marked the historical beginning of the development of modern colliders. By its very nature, a collider is essential in increasing the energy related to the emergence of new particles. Higher the collision energy, the better the quality of the facility that produces it. The energy used for generating new particles is called center of mass energy. The primary task of a collider is to increase the energy in a center of mass system to its maximum. And the first hadron collider, well, NICA is a hadron collider. That is why I will give you some examples of mainly hadron colliders. The first hadron collider was built at the European Organization for Nuclear Research, also known as CERN. This hadron collider consisted of intersecting rings which accumulated charged particles. The circumference of this facility was approximately 470 meters. It was used for the collision of 30 giga-electron-volt proton beams. In the center of mass system, it corresponds to 62 giga-electron-volt collision energy. What are 62 giga-electron volts? The same 62 giga-electron-volts may be obtained with an extracted beam experiment, but the energy would have to be equal to 2 tera-electron-volts. Instead of 30 gigaelectron volts, we would have to provide 2 teraelectron volts. This is about 100 times more energy than that of the accelerator. What does that mean from the viewpoint of the accelerator's size? If the circumference of the first hadron collider was less than 1 kilometer, then, for instance, the first accelerator to achieve the energy of 1 teraelectron volts, which was the Tevatron in the US, had a circumference of 6.3 kilometers. To reach the energy of 2 teraelectron volts, one would have to build an accelerator with a 12-kilometer circumference. Here one can see right away the payoff from doing experiments on colliding beams. We build a much more compact facility and attain much higher energies. This development path for colliders has persisted for a very long time. The biggest collider, the Large Hadron Collider at CERN, is based on this concept of increasing the energy of collisions. What is the most amazing feature of the NICA collider? The NICA collider is being built to be the lowest energy collider. Even in the case of the NICA collider, the center of mass energy, of course, increases. For example, an extracted beam experiment is planned to be conducted at the NICA complex, called baryonic matter at nucleotron. In this experiment, the nucleotron beam will be directed toward a stationary target. The center of mass energy will be 3.4 gigaelectron volts per nucleon. If the same beam is used for the experiments on colliding beams, the center of mass energy will be around 4 times higher, approximately 11 gigaelectron volt per nucleon. There is a clear energy gain, but this gain is somewhat conditional. In fact, such experiments, similar to the ones that are planned to be conducted at the NICA collider, will be carried out, for instance, at the international facility called FAIR, or the Facility for Anti-Proton and Ion Research, in the construction of which, in Germany, Russia also takes an active part. One of the experiments at the FAIR facility will be conducted on the collision of heavy ions, accelerated in a synchrotron with a target. The circumference of the main accelerator in the synchrotron facility, which delivers the beam to a stationary target, is approximately 1 kilometer. It provides about the same level of center of mass energy as the NICA collider, whereas the NICA collider is around 500 meters. But it's not just one accelerator facility, but rather 2 accelerator facilities with 2 accumulative rings. Therefore, if we speak about saving space and costs, it is not known which facility is cheaper. Why did one come up with the idea to build a collider for such low energy levels? One may assume that the experiment on a collider is more efficient. Surprisingly, I will demonstrate that it is not true, but rather that it is exactly the other way around. The experiment effectiveness is defined quantitatively with a certain parameter called luminosity. While conducting an experiment, we study the emergence of certain particles. What is luminosity? It is the probable rate of particle production in a given collision, which we are trying to study, normalized by the cross-section of the reaction. A cross-section of a reaction is, plainly speaking, the probability of the emergence of this particle in the given collision. A cross-section is measured in square centimeters. Luminosity is the rate of particle production divided by the cross-section of the reaction in which these particles emerge. This value is a unique value for defining the effectiveness of any experiment. It is measured based on its definition. Let's say one is to measure the reflection of incident particles at a certain angle. The cross-section of such a reaction has been known from Rutherford's time. The number of particles emitted on a given angle is calculated and normalized by the cross-section. Then, to determine how many rare events will be generated, one takes the luminosity value and multiplies it by the cross-section of the reaction that is to be studied. This way, we determine the rate of the possible generation of those events in which we are interested. That is why luminosity is one of the major characteristics of any experiment. There is a certain technical limitation to the maximum value of luminosity, which is related to the work on accelerated particle production. Of course, one wants to get the maximum luminosity, because the higher the luminosity, the faster the statistics are collected, which are needed to ensure the accuracy of the research. There are also limitations related to the particle production rate. As Mikhail Luminosity has taught us, when a certain amount of something emerges in one place, the same amount disappears in another place. That's why particle generation in an experiment is exactly equal to the number of particles lost in the same experiment. Accelerated particles don't accumulate anywhere. Therefore, an accelerator generates accelerated charged particles, and the experiment destroys them. The same amount generated by the accelerator is destroyed by the experiment. The loss of particles in an experiment is related to those useful events that are studied in the given experiment and to the losses arising from other processes. A well-designed experiment is an experiment in which other losses amount to a small part of useful events. In this sense, for a well-designed experiment, luminosity is approximately the rate of generation of accelerated particles divided by the cross-section of the studied reaction. Or one may say it is the upper estimate of luminosity given the parameters of the accelerator that generates a flux of accelerated particles. In an experiment with an internal target, one may express luminosity in terms of the parameters of the very target. In this case, luminosity is defined as particle flux, directed on the target, multiplied by the target areal density. Target areal density is measured in atoms per square centimeter. Accordingly, by varying the target areal density, under the same flux, one may approach the marginal luminosity that may basically be attained by an accelerator facility. Speaking about the NICA accelerator complex, for a fixed target experiment, for example, the nucleotron will be subjected to the following cycle. During approximately 5 seconds, a gold ion beam will be accelerated. The next 5 seconds will be spent on the slow extraction onto the target, and about 10 to the power of 9 gold nuclei will be accelerated during one cycle. This corresponds to the gold nuclei flux per unit time, around 10 to the power of 8 per second. Here are these 10 to the power of 8 per second. The cross-section of the following reaction amounts to 10 to the power of minus 24 square centimeters. This number was told to me by physicists. Actually, I understand roughly how it is obtained, but it may be taken as axiomatic. With such a flux and such a reaction cross-section, our maximum luminosity is limited by the value of approximately 1.5 times 10 to the power of 31 centimeters to the power of minus 2 seconds to the power of minus 1. To achieve this luminosity, the thickness of the target must be around 10 to the power of 23 atoms over 1 square centimeter, which is easily attainable for gold foil. In general, this experiment provides good luminosity. Next, the thickness may be limited by the disrupting effect that the target has on the beam. The maximum luminosity may also be limited by the detector capabilities on event processing. In any case, the stationary target experiment within the NICA complex could potentially provide up to 10 to the power of 31 luminosity. So how does this relate to the collider experiment at the NICA complex? The main luminosity limitation in the collider experiment, and perhaps this distinction between a colliding beams experiment and that of a stationary target experiment, is the detector structure. At the colliding beam facility, first, the detector is limited by its inner space for the installation of the subsystems. And over the years of the development of collider detectors, a specific design was developed and has been built, which is generally accepted for its construction. Specific electronic devices are used for particle tracking. For example, in the multipurpose detector, which will be in operation at the NICA collider, the maximum event rate is limited by the electronics just in this system that calculates the particle trajectory, which is approximately 7 kHz. If events occur faster, then the detector simply won't be able to register them. That is why, in the technical requirements for the NICA collider, the luminosity is defined by the level of luminosity that would provide the maximum load of the detector. We take the event rate registered by the detector and divide it by the reaction cross-section to get 10 to the power of 27 centimeters to the power of minus 2 seconds to the power of minus 1. It is 4 orders of magnitude lower than in the fixed target experiment. And here, I believe, from this moment on, one will always wonder why one should build such a collider, which, firstly, doesn't advance in terms of energy compared to the internal target experiment, and secondly, has much less luminosity or much lower productivity than the fixed target experiment.